Hello, everybody. We are going on creating our own small little toy language. So last time we looked at grammars and the way they are kind of written, the way they are organized and what the different parts of them mean. And this time we are going to, well, first we are going to look at a little bit of a presentation. It will be short. And we are going to finally look at some code. I know it's the third webinar in the series, and we are going to look at the code only now, but that's how it is. As usual, if you have any comments, any questions, you can put them in the chat in Zoom, and I will probably make a little break like in the middle and look at them, or we'll just go to the end and I'll answer whatever you write down there. Okay, so today we are looking at the way how we can create a lexer, which is a part of the parser of our interpreter. And the lexer is dealing with the lowest level of grammar. So terminal symbols, things like numbers, variable names, keywords, operators, anything which is like an atomic thing, indivisible, okay? So let's go over a little intro here and look what we are going to be dealing with. Okay, so let's say we have an input like that. I don't know if there are any fans of Douglas Adams here. Douglas Adams and his Hitchhiker's Guide to the Galaxy. 42 is what I always use. Okay, so that's because I love the book. If you haven't read it, read it. It's awesome. Okay, back to the business. So let's say we have an input like that. So we have binary expression, 42 plus 10. And when we can apply our grammar to this expression, what we are going to get in the end is something like that. So it's a binary, the operator is plus, and there are two operands, two integers here. But these things here are all actually non-terminal symbols. So they are described in the grammar of our language in terms of other symbols, which are lower, kind of have a lower order in the grammar, if it makes sense. And our literal expression here, it's actually a number. More specifically, it's an integer number, but for now, let's say it's a number. And a number is a sequence of digits. And of course, every digit sequence consists of, well, individual digits. And all those things are described in the grammar. We are going to look at this grammar in a bit after I finish here with this introduction. And since we are focusing on the Lexer today, this is what the Lexer sees in this input. So it's going to, when we run this string through our Lexer, this part of the parser, it will tell us back, okay, so what you gave me is a number followed by an operator and followed by a different number. Well, it doesn't really care if it's different or not, it's just a number. And the way we kind of do this, the way we separate our a huge input string into those small indivisible atomic parts is via a process known as tokenization. Oops, yeah, tokenization. It's used not just in programming languages or compiler design. It's used basically, the same process is used every time you need to parse anything. Like, for example, if you have something, some library which processes a command line input, for example, you will have to tokenize the input, the string, into separate smaller parts. And let's take a brief look at how it works. Again, this is our input string here. And what we have is we need to have basically two positions when we want to tokenize some input. The position where we begin and the current position in this string, in the input string, which we are going to move. So in this case, we start like at the first character string, and it's a digit, it's a 4. Okay, so we look at it, we see a digit, and here we can decide what kind of rule we are looking at. So since the first character is a digit, the only thing we can have here is a digit sequence. So makes sense. So the way our Lexer is going to work, it's going to enter from an entry point, look at the first character it encounters, decide where to go. Of course, it will skip white space characters first, but that's we'll take a look at that. And it will decide based on the first character where it should go next. In our case, yeah, digit sequence numbers basically. And since the sequence will kind of continue for as long as we move our position, which is movable, and for as long as we see at this position another digit, it will continue processing a digit sequence. So in this case, we retain the first position where we started and move this window kind of a one character wide window to the next character. So we see a digit again. So we stay inside the digit sequence. We continue until we run out of digits, basically. So here, as soon as we move to the white space which follows the number, it doesn't have to be a white space. It just has to be something which is not a part of this digit sequence rule. Basically, any separator character. Okay, so here we have run out of digits, and so we collapse this entire thing from 4 to 2, basically to the end, into a number. The number, of course, is going to be 42, and if you see that little arrow there, we abandon our first position from which we have started initially, and we move it, we collapse we collapse the scan window, let's call it a scan window, something. So we collapse it and we go past the number. So, and here we have the first little part of our tokenization effort. It's a number. And what we have next, we have a space, and it's a separator. And in our language, since we are not making it Python, we are going to ignore white space characters completely. So they are meaningless. We can omit them. We can add as many of them as we want in between meaningful parts of our input. So it doesn't matter. So what we could have had here, instead of one white space, we could have like, I don't know, 5 tabulation characters and 32 spaces, and we would skip them all at this point. So yeah, separators, we go and skip. And we move on. Again, we move to the next character, and it's a plus sign. So again, our Lexer will enter from here. It, of course, remembers its current position, the starting position. It will look at this character. It will see a plus. It will decide, okay, it's an operator. Let's go and fetch us the operator. So it's an operator. And again, we skip the white space, and again, we skip, we kind of process the digit sequence. After that, we get the number 10, and here we arrive at the end of the input stream. So it's an end of file. We don't necessarily have to have a file. Actually, the Lexer doesn't even care if we have a file or not, but the end of input will be marked as the end of file, a special end of file tag. And all the way as we go, what we get as a result of this work the Lexer does, we get so-called tokens. So every little piece of input is a token, and a token is a value which is a substring basically from the input, which relates to this specific part, and this tag, a classification we assign to it. So we distinguish between integers. We will have floating point numbers. We will have Boolean literals, true, false, variable names, operators, punctuation symbols, and keywords. And we will kind of be able to distinguish between them all. Also, the way our Lexer works is going to be lazy. So it's not like we give it an input string and it tokenizes the entirety of the input. No, this is kind of counterproductive because you have to have some storage for all those tokens which you don't necessarily need after you have lexed the input. And you know, why would you do that unless you are going back and forth along this collection of tokens? So we will go into grab one token at a time, and the Lexer will have instructions from the outside or when to move and when to grab the next token. And then also we will have an ability to preview one token forward. Okay, so let's now see how it's going to be done in our language. So I don't need this PowerPoint anymore. We are going to move into Visual Studio. I have here a project which I have created for our language. It's already kind of operational. A simple CMake thing, which just has manually added files and if you're interested, you will have this project later anyway. So we have here kind of a library, a static library, which will contain all the logic of our language, and an executable file, which will just link to that the entire thing and just use it. So the executable application is kind of simple. Okay, so what we are looking at here is first and foremost the token. It's simple class, and the first thing, the most significant probably thing we have in it is this token kind. It's 1 byte, but doesn't really matter whether it's 1 byte or whatever. So these are all the tags which we will have. These are all the symbols we support. So, well, first we have here an error symbol, which is, well, unknown. It's an unknown token. We don't know what it is. It is not a part of our language. So this is the, well, end file. So it's a plus. It's the addition operator. It's a subtraction operator, or a unary plus, unary minus. This is multiplication. This is division. This is going to be our assignment thing, because we will have variables in our language. This is the equality operator, which we are going to kind of look and steal from C++, C, and other similar languages. It's less sign, of course. Well, I guess names of these tags are kind of self-explanatory, but I'll just write them here anyway. So we are on the same page here. Okay. So this is a greater sign, less equals, greater equals, oopsie. We will also have logical operators, again, stolen from C++. Not equal, unary negation, logical negation. Well, of course, this is our opening parentheses, closing one, our comma, which we are going to be using for function parameters and function calls, semicolon, which is our terminator of declarations and statements, and we are going to look at those when we get to the parser, which is going to be, I guess, iterative. Those things you are familiar with, they will signify scopes and function bodies. Identifiers is, well, it's any name, I don't know, AB, whatever. Integers are like, integers. Floating points, we will also have just your normal floats. We will have keywords, true, false. These are keywords, by the way. I just named them starting with KW here in this enum, so it's kind of obvious. Yeah. And we will have type keywords. We will have ints. We will have floats, bools, We will also have a special case. We won't have a type void in our language, but this thing, this name void is going to be very important when we get to functions. And the way we define variables is going to be with the keyword var. And the way we define functions is going to be with the keyword fn. I'm a C++ programmer, and I also took part in creating a parser for C++. And to be completely honest, I'm sick and tired of this ambiguity in C and C++ that we have, where we don't really know if we are looking at a declaration of a variable or a function, which is a big problem, which also has a name, most fix and parse. I think I mentioned it last time. And the way it could be solved, like really easily, is having a keyword for function declarations and not declare them like variables starting with the type name. So yeah, we are going to have that here, and we are not going to suffer from ambiguous grammars. Okay, our keyword turn for functions, and we also will have if statements in our language with else clauses, which can be like in a normal language, we will be able to chain them. Like we can write if something, if else something, if else other, else, and so on. And we will have one type of loops. It's a while loop. So over the next meetings that we will have with you, we will implement everything here, and we will create an evaluator. Okay, so that's all for the tag for now. Let's take a look at the token class. So our token will have two essential data components. The value, which is a string view. It's a substring from the input. And this tag thing. And of course, we will have two service getter functions here. So that's all about the token, basically. Okay, a couple of words why we have a string view here. And isn't that kind of dangerous? Because, you know, if the input is taken away from you for some reason, you will have all those dangling string views running around in your program, right? Well, actually, this is by design. And the requirement we will impose on our language, well, not the language itself, on our interpreter of the language, is that once we get any input, we will keep it until the end. So no matter where we get this string we are reading with the code written in our language in it, it should live until the very end of the execution of our program. Because this is the most logical and convenient way to do that. We could, of course, take parts of the input, create strings, store them somewhere, but that's more trouble than it's worth. So yeah, for the price of keeping like the contents of the input until the end, we will have a kind of clear and convenient thing to deal with substrings in that in what we get. And also tokens anyway, they don't really go anywhere. So we read them in our parser. We maybe take parts of them, store those parts somewhere. But for the most part, tokens are taken from the Lexer, looked at, and discarded for the most part. Because they we don't need them past the point of deciding which grammar rules to apply. Okay, so that's the token. As you can see, it's really a simple data structure. Basically, it's a dumb data, not really a proper class. Okay, and yeah, and this cheeky statement here is going to be for us to enable like using those names from the token class itself. We can write here, not here though, token. So we will kind of import the contents of this enum into the token class itself. Okay, so now let's go and take a look at what our Lexer is going to look like. I think I mentioned it last time that I was contemplating whether or not I should live code or just use a pre-coded project here, and I decided to use the pre-coded one because you don't really have to sit there and look at me typing. It will take a lot of time. So let me know, by the way, if you prefer kind of looking at me typing, or if this format is totally okay with you. Like when we have already coded things, and I will just go over them, explain them, and we will also run the thing at some point and look at what happens in the debug. Okay, so let's talk about what our Lexer will actually need to have as its working state. It will need basically to keep track of three things. Input we are looking at. It will have two iterators into this input. Like in the presentation, I showed you this arrow and rectangular window which looks into individual characters. Those we will do using screen view iterators. Also, since we kind of want to have an ability to preview the next token potentially from multiple places in our program, we will have a storage of one token which will be kept there until consumed. So this is what the optional for. And if we look at the actual data members, so here's our buffer. Those are our iterators into the buffer, which we are going to move and remember where they stay. And this preview optional. And the way this preview optional is going to work, whenever we are asked to look at the next token, we are going to check if we have one cached. If we do not, we tokenize a part of the string and store it in this preview. And whoever asked us to like preview the token, they will receive an answer from us. And every time they ask us to preview the next token, we will give them the same stored thing until they asked us to consume the token. So the interface of the Lexer, if we look here, this is the peak function, which does exactly that. If the optional with the preview is empty, it will fill it by tokenizing the next part of the string, and it will return a reference into it. If it's not empty, it will just return a reference into whatever is stored. The token is stored in the option. And this next function, it will take the contents of the preview, take the token out of the preview, clear the preview, and return the token that was in there, like by just returning by value. So the operational procedure with the Lexer from the outside user's perspective is you can either call next until you start getting the end of file token, and that will be returned once we reach the end of the input. So the Lexer, even if you reached the end of the input, it is safe to use the Lexer's function. It will never crash. It will just give you the same answer again and again and again. It will give you end of file, end of file, end of file, and it's going to be basically the same thing you get. So the operational procedure here. You either call next, and once you get end of file, you stop, or you call peak, decide what to do, go there, call next to drop the token because you don't really need it anymore because you have decided based on it what to do. And again, you do that until the end, until the end of file. This is what our parser is going to be doing, really. We will look at the parser at a part of the parser next time, basically. But yeah, that's what our parser is going to be doing. It's going to be picking all those tokens from our Lexer, and yeah. Okay, so we got one answer in the chat that discussing code is fine. I think, yeah, I also think it's kind of better because looking at someone typing is boring. I know. And since it's live, we cannot really kind of, collapse the part, make it 10 times faster. Okay. And here's the public interface of our Lexer, basically. We have the operator. That's not necessary. I just kind of, I like calling it kind of like a function and feeding input into it. So this is the operator we will use to push input into the Lexer. And if you look here at the constructors, the constructor, we only have one, and it's by default. So we are not providing any input here. And the reason for that is the Lexer is lazy in all respects. It is also lazy to be initialized because you can create it somewhere, wait for the input, and then seed it with the input. So we do not tie our Lexer into a specific input stream. We can redirect it to other inputs. So one object, we can just replace its string it tokenizes. Okay. Next and peak, I've already told you about. We will look at them at their internal implementation, and we will also run them and see how they work. And those are all private parts which are for internal usage. This function here, next, everything goes on in there. So all magic happens here, and basically what it does, it uses all those things here. So this good function, it will determine whether or not we are at the end. So if it returns true, we can go. If it returns false, it's an end of file. Inside the Lexer, we will preview the characters. We will be able to advance iterators. We will be able to read the token string between those iterators we are keeping track of. So when I showed you in the presentation this 42 thing, what we would have there is one iterator pointing at 4, the other iterator going boop, 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 and then it starts pointing to the space. And the value of the token is like whatever the part of the string between those. Well, skip spaces, of course, because we don't need them. This function consume, what it does is it will take the string between our iterators, assign the tag we provided with to that string, construct a token from it, and it will collapse the iterators into one another. So our begin iterator, which was at the beginning of the token, it will just move to the end. And that's our new current position. It will also skip spaces. And those things are for different kinds of entities we can get out of this. So those are basically our terminal symbols combined into broader categories. And let's take a look at how it works. Well, first of all, I have a bunch of service functions here, and they are needed so that we do not clutter our Lexer code with checks. So what they do, those functions, they take a single character as an input, and they answer the question, does this character belong to, say, a number? So is it a digit? Is it a letter? Is it maybe some separator? Is it an operator character? So let's say if we get plus, the is operator will return true. And this is needed to avoid writing everywhere inside the Lexer functions, things like big character if this character equals to A or B or C or whatever, then and so on. So it just makes the code kind of neater. And this this function is in range. What it's needed for, I will show you what it's needed for. So let's say we have, what is it? Is ID char. It doesn't work here this way. So, okay, anyway, the thought process behind this function was that we give it a character and we give it 2 iterators into some array, and we ask, is this character in this array? And let's say we had a long string of every letter in the English alphabet, and our isLetter function could kind of answer the question whether or not our current character is a letter by just searching for it in the string. I guess it's not used anywhere, I think. But anyway, so that was the thought process. Maybe, yeah, here it is. So here we have an array of all operator symbols, characters we have in our program, in our language. And we can answer the question by searching whether this character here is inside this array, if it's present. Yeah. And also, there is the topic of keywords. Okay. If you look here, we have a number of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 keywords. Big language we have here. So yeah, all those keywords, they look like identifiers, really. So they are just words, and we need to recognize them. And I did it here in the dumbest way possible, really, by creating an unordered map, static unordered map, putting strings as keys and token values, those tags as values. And it allows us to add keywords to the language if we need to really fast. We just need to define this tag and kind of add it here. And so we have a keyword. Of course, deciding what to do about this keyword is another matter, but in terms of the Lexer, adding new keywords is like super easy in this case, by having them just a dictionary basically of pre-classified strings. But it's not the most efficient thing in the world, because what we have to do in this case, whenever we get any identifier in our program, we will have to go and look it up in this map and decide, maybe it's a keyword. But this part, I think we just don't need to bother at this point, because honestly, it's a small language and it will not have like a huge problem with performance because of that, if it will have any problem with performance, to be honest. So I just left it here. An alternative way of catching keywords would be building like a state machine where you switch states based on the characters you're looking at in sequence. So let's say you tokenize your input and you have the letter R at some point. So yeah, I've got a comment that I handle keyword lookup the same way. Yes, we handle it the same way in C++ really here, so it's not a huge deal. Just know that there are alternatives if you really, really need them. So the state machine would do what? So let's say you have the letter R, and you ask your state machine, is this a keyword character? And it goes, yeah, we have a keyword which starts with R. So we enter the state where we have R. You go next and you have letter E. And again, there are transitions from this R state to the E state, and we have RE and so on and so forth. And you have this huge state machine graph, which gives you paths. And if those paths terminate in not in rejection of the input, then you have keyword. But it's a complex thing to do. It would be clumsy. Okay. So yeah, this map approach works, and it's super easy. All right, so let's see what the functions of the Lexer do. Well, of course, our constructor will just initialize things, our iterators from an empty stream view, which is there by default. And the only thing the operator, our operator, which we are going to seed with input, does, it will just initialize the buffer and initialize the iterators. So in the state when we have just fed it some input, both iterators start and end will point to the same thing, to the same character. Also, we will reset our preview optional just in case we had something there already. Like we were working on some input stream and then we decided that, okay, discard that. Here's a new input stream for you. So it will clear basically the its stored token. And this is a trim, so we will just go and skip any leading spaces we might have in the input. And skip spaces thing, well, it really is nothing special. So while we still have input and the next character we are looking at is blank, meaning a space, a new line, a tab. There's a number of them. Let's look at them real quick. So it's a space, it's a new line, it's a tabulation, it's whatever those are. I've never used them really. It's an R, which is also kind of part of new line in some systems, and it's just a terminating null character, basically. So those 1, 2, 3, 7 characters are blanks. Blank means ignore, basically. And while we are looking at some kind of white space characters, we just go and move our iterators forward. This advanced function here, it will just move the end iterator. So the end iterator, again, is the one that moves. The start we keep at position, and we move the end until our current meaningful token ends, basically. Yes, and here we collapse them. So if I don't even know if I have to like explain it in detail, but yeah, we have a beginning of our input. We have the current position, move, and then the beginning moves to this current position. Okay. So, well, let's go like kind of from the, let's go after the meaningful parts first. So this next function, it will call this peak. And as you can see, it will just take the token from it. It will, by copy, it will reset our preview optional and it will return whatever it's got. And so this peak function is our main bread and butter logic of the Lexer. It's entirely there, basically. And here's what it does. As I said already, if our preview optional is not empty, we just return whatever is there. So our users can look at the same token multiple times without really any cost, except the initial tokenization of it. If we have reached the end of our input, this is where we just return the end of file token every time. And next, our grammar starts, basically our grammar. So let's take a look at the grammar real quick. So what interests us in terms of the Lexer are basically terminal symbols. And our terminal symbols, this is already kind of a non-terminal one. Our terminal symbols are identifiers, different kinds of operators. So we have plus minus. We have relational equality operators and so on. The names identifiers, they are defined like this. So our identifiers need to follow specific rules, right? And in order to be valid, this is what we require as designers of the language. And in our case, what the identifiers will be allowed to have in them. They will be able to have letters from, well, basically from the English alphabet, from Latin alphabet, A to Z, case sensitive. They will be allowed to have digits inside names, so we can use digits in the middle of name. And they will also be allowed to contain the underscore character, this one. But, by the way, copy paste give me but the name, any name, is not allowed to start from a digit. It can only start from a letter or an underscore. And so the identifier is defined like that. To have a valid identifier, we have to have either a single character, which is in this set, in the identifier start set, or we can have this character from the identifier start set followed by a sequence of characters from the identifier char set. This way, we distinguish between the first character of any name and any subsequent characters of that name. And it allows us to not have any problems with ambiguity between numbers and names, basically. Because we can have identifiers which start with digits if we choose to write our grammar this way. But this grammar will be not really convenient, let's say this way, because we will have to then adjust on the fly to the reality. So if we look at a character, see a digit, and our names allow digits, we go, maybe it's a number, maybe it's a name, and we go read those digits, and then we see a non-digit, and it's a mess. So it's better to just disallow ambiguity in the grammar, basically. Okay, so for numbers, we will have integers and floating point numbers. And if you look here, What it really looks like is something which I just said you that we didn't want to have. Well, technically it's an ambiguity because both integers and float numbers start with the same thing. So we do not know in advance whether or not we are dealing with ints or floats, but that is a path to the most vexing parse kind of problem. But in this case, it really doesn't matter because we can deal with it like really easy in the Lexer. We cannot necessarily deal with a similar situation later in the parser when we start working with non-terminal symbols and complex structures. But in the Lexer, it's not a big deal. You can have it somewhere. Okay, so yes, and those are just digits and digit sequences. And this is the subset we will take a look at right now. So let's go back to our Lexer and let's see. So the way it goes is we check what kind of character we are looking at. And if it's some specific kind of characters, we just say, aha, this is that kind of a terminal symbol. So we will just go inside the function which produces a token for this kind of specific terminal symbol, and we will just return the result. And the result can be either a valid token or an error. I will show you an example of an error a bit later. And we have like groups. If it's a character which can be the first one of a name, it's an identifier. If it's a digit, it's a number, which covers both floats and ints. If it's an operator token, it's an operator, of course. And if it's a separate token, it's some kind of punctuation. It may be an opening curly brace or parenthesis or whatever. It can be a comma, it can be a semicolon. And of course, by default, if we have none of these, it's an error. Okay, so those functions, they really look like similar. Now here's our identifier, for example. What happens here? Okay, so we have already decided that we have potentially n identifiers following this, right? So we know that the first character is already a valid kind of identifier character. So just decide, like we say, okay, let's assume that we will have an identifier right now before, like in front of us. And while we still have input, we are going to go forward in a loop. And this loop is going to continue until we either bump into a separator of any kind, or we reach the end of the input itself. So it's a loop which goes like this. We take the next character from the input. If it's separator, we break. Otherwise, we just move to the next character. If it's an ID, okay, we continue, and so on and so forth. And we just go like that. We just go inside a loop like that. And if we have like anything other than that, we will just have an error, which in identifier probably will never happen unless unless we add something like really bizarre there. And the separator, of course, is parentheses, curlies, semicolon, blank symbols, commas, dots, or any kind of operators. So we can write code without spaces between names and operators language, as we can basically anyway. Okay, so that's the identifier. For numbers, again, if we see a digit, we can decide, okay, we will go into we will go and try to process a number. And here we will assume first that it's an int. And while we have digits, you get the idea by now, I think. While we get digits, we just keep going in the loop. But our floating numbers contain a dot inside of them. So if it is still an integer we are looking at, and we have a dot, we say, okay, it's not an integer anymore. It's a floating point thing now. And it's floating point number now. And this result, you see, we set it to float number. And if we bump into a second dot, it's, well, technically it's an error, but it's not a Lexer's problem. Because if someone writes like 1.2.3, right? What the Lexer will give us is a float number, 1.2, a dot, and an integer 3. And it is going to be a parser's problem, basically, from this point on. And by the way, in the identifier, I said that it's really incredible that we bump into something which will break our identifier. Yeah, the indication of that is that I forgot to break here. So when I was debugging, I never got here, basically. So with different inputs. Okay. And for operators, we have two kinds of them. We have like a single character operators and we have a multiple character operators. So let's say plus is just a plus. It cannot, whatever it's surrounded with, it's a plus still, it's just one character. But for things like equality sign, right, or this exclamation mark, they can either stand on their own or be a part of a bigger operator. So we can either have like just equals, or we can have equals equals. And our Lexer is lazy, but it's also greedy. So it will consume the largest sequence of characters that it can. Now, if you put two equality signs side by side, it's going to be this operator equals equals. And if you put three equality signs, it's going to be an equals equals operator followed by just a single equals operator. So we consume as much as we can first. And for if we look at the thing and decide it's an operator, what we can do here is this basically. So we have a list of all operators here, of all possible operator starting characters. And when I talked about keywords, this is basically what I meant, but more elaborate than that. So if you look here, we look at the first character of the operator and we say, it's a plus. We cannot have any more complex than a plus. So it's a plus, minus, and so on. But if the first character is the equal sign, we have two possibilities here, right? And we say, okay, if it's an equal sign, let's take a look at the next character which follows that. And if it is also an equal sign, then it's going to be this equality operator instead of assignment operator. Otherwise, it's an assignment token, kind of. It's either equality or just a single equal sign. Same with not equal. We can have, if our exclamation mark is followed by this equality sign, then it's this operator which is not equals. Otherwise, it's just a unary exclamation point, and so on. And for those two guys here, for and or, we can only have two of them. So we cannot have one. And here, just if we have this ampersand, we look at the next character and see, okay, it's an ampersand. If it's an ampersand, it's a logical AND operator. Otherwise, it's something weird. I don't know what it is because I don't have a single ampersand thing in there. And this operator continue function, what it does, well, it simply looks at the next character. If it matches this thing, then if it doesn't match this thing, it returns the alternative thing we gave it to. We gave it. So in this case, let's say we have just a single equal sign. We go here, and it's followed by, I don't know, like digit 1. So we take a look here. We do not see the second equality sign. We see a digit, so it's just EQ sign. And if we see the next equality sign, in this case, we move our seeking iterator forward. And we say, yes, indeed, it's a double equals thing. Okay. And every time we perform this kind of logic, what we do is, if you look here, every one of those functions has this consume call at the end. And what the consume function does, it's an important part, really, of the Lexer because it processes the way tokens are created. So if we told it, we have an error token, what it's going to do. So we'll look, so let's say we are looking at a number and we see 1, 2, 3, x. And x is not a part of the number, and it's not separated with anything from the digits. It's just kind of glued to the last digit. In this case, this token is something we don't know because we cannot have like something other than separated there. And we say, okay, it's an error. So in case of an error, what it's going to do, it's going to move forward until it bumps into any separator or the end of input, and it will basically just take this entire thing it just went over and will create a token with it as a value, and it will tag it as an error. Okay, otherwise we just, read a string, just have a string view between two iterators. And if if our token we are looking at was an identifier, here is what we are going to do is go into our keyword map and check. Maybe this identifier is actually a keyword in our language, predefined one. And if it is, we just switch the tag basically to the whatever the keyword we were able to look up. Otherwise, it just remains identifier. And yeah. And if this tag is end of file, end of input, we'll just have a token with the end of input, end of file tag, and empty string in it. So basically, that's all. And of course, we skip spaces to the next kind of, when we read any token, we skip spaces to the next meaningful non-blank character. So we do it right there. So we don't have to start with it every time. And of course, we initialize the preview, because the only way we get into this consume functions by any means if the preview was empty, because otherwise the peak function would just return whatever's kept in there. And we return, of course, the contents of the preview. So create a token in this, our optional, and it becomes our currently actively cached token. Okay, and now let's go and take a look how it works. So here I have this test Lexer function in our entry point in our executable part. And here I have written for you a lot of things with some kind of a, let's call it a joker inside. And what this function is going to do is going to create a Lexer, seed it with the input we gave it, and really until we reach the end of input, which is processed here, we will go in. We are going to just grab the next token every time. So let's, I guess, take a look at the way it works. Breakpoint here. Let's go inside. We will, of course, need to compile it because I put all those, comments into the token. But anyway, so the Lexer is now initialized. So as you can see, it has the buffer of the input we gave it, and the start and end iterators, they both point to the beginning of the string. Now let's go inside the next. And by the way, what is we will have the equality operator here. So let's go inside this next function and take a look at it. Well, of course, we will get into the peak first, and since we have just started, it's empty. So since it's empty, we are going to go and dig deeper. And our next character is, well, equal sign, as you can see. So we are going to skip this ID. We're going to skip the digit. We are going to get into the operator. Is operator here. It will return true because our equal sign is inside this array. And we will go here. So picture, it just looks at whatever is at the current point, or it will return a 0 character if it's end of input. Okay, we advance, and now if we look at, let's see if I can do it this way. So go this. I don't know if you can see it very well or not, but the start iterator still points to the beginning of the input, but the end iterator has now moved one character to the right, so it's pointing to the second character actually in our input. That's what the advance does. It just moves the end iterator one character to the right forward. Okay, so result is error for now, but we know that we have the equal sign. So we will get here, we have an equal sign, and we go inside this continue function, and we will pick the next character. So this thing we are looking at is the second character in the input. So our input begins with equals equals. What we're looking at is the second character, and it is really the equal sign. Okay, so we advance, and now our end iterator is looking past the second equality character. So basically our end iterator is here now at this space. Okay, and so we return, it was a double equals. Yes, so it's an EQ, not just EQ sign. If we go inside, our kind is not an error. We will go just read the token string, and we have read this equals equals thing. So it's not an identifier, so we skip looking up keyword. The value of the token is going to be equals equals. We of course skip spaces. So now at this point, once we move past this skip spaces call, what we are going to be looking at is that point here. And the preview, it was empty, and now it's not empty, and now it has a token which has a value of equals equals and tag of EQ. Okay, and we just return the contents of the preview. And now we immediately reset preview because we called the next function. If we called peak in that loop, we would just loop forever until we called next. Oh, that's that. And we return the token here, of course, and this switch is going to handle all the different kind of things. It will just categorize them for us. I will just start it and let it go to the end. I'll just continue here, and I will show you the output. So what this function did for us. So we had this input with all those different kinds of things we wanted to look at. And as you can see, they are categorized. So equals equals is an operator. Oh, technically, of course, it's not just any operator, it's a specific operator, but I think for debugging purposes, it will be okay if we just group all the operators into the same category. So that's the exclamation mark, that's an unequal, that's the and, or, less, greater, and so on and so forth. And here is the joker I promised. When I told you about this loop and breaking on error when we have something unexpected, I kind of used the example of a number. And here we have a number which has a character there attached to it, which doesn't really belong here. Here it is. This is the number here. And this is an error. So it goes against the way numbers are defined. And since it starts with the digit, we assume it's a number of some kind. Okay, so, and yeah, as you can see, errors, and we are, by the way, when we get to the parser, we are going to talk about error handling in parsers and how it can be done so we do not break like the entire parsing process. Errors are, by necessity, they are designed in the way that they do not obstruct our ability to go forward. So if we bump into some error along the way, we just do something about it. We kind of fixate that, okay, we had an error, but we continue moving. This way, if, let's say, we have multiple errors in our code, we can catch, hopefully, them all instead of just breaking on the first one. And the Lexer follows this same kind of philosophy. So, okay, we got an error token, big deal. We just report it. Yeah, and it goes forward and forward and forward, and here are keywords: true, false, var, fan, int, float, bool, and so on. Okay, and as you can see here, some things are separated by spaces and some things are written like densely here. It doesn't really matter, but what I wanted to show you is that you see there's a plus and immediately after that is a minus. But a plus is a valid operator, so we don't care if something is really next to it. So we just report it's plus. And it allows us to write things like a plus b without spaces, if you are into this sort of thing, of course. But it doesn't work here, of course, with this number because s is not a separated character. Okay, so that's the Lexer for you, basically. And the next time we are going to write a parser. Well, I'm not going to write it, I will have it, but yeah, we are going to have a parser. And the parser itself is kind of ready, but I want to start small first. So I guess I will just modify it and make it into an expression parser which will work on a limited subset of the language so we can get a taste of it. And then we will go into the real thing, to the real thing. So yeah, that's the plan for the next time. We are going to have an expression parser. And we are going to go and create an expression parser, let's say on a conceptual level. So we will not have any syntax tree yet, but the syntax tree will be after that. So we first look at how parsing is done, then we design the syntax tree for our language, then we add different things like variables and functions, and then we add semantics and evaluation. So that's going to be the plan for the next, I don't know, several months. Okay, so questions, comments. How to handle the situation where it depends on the context, how we tokenize the input. For example, the double right triangle what do you even call this symbol? So it's basically greater operator, the stream reading. Well, there are several ways of doing that. One of them is called a Lexer hack. When you tell the Lexer, look, here in this context we are in, let's say we are in the middle of expression, right? In a binary, and we are looking for an operator. In this context, go for this double thing. And the Lexer then will tokenize the thing differently based on what you tell it from the outside, from the parser. So that's one way to handle it. The other way is that the Lexer will always do like two separate operators. And then in the parser, you will have to uglify your Lexer because you will have to have probably previews like farther than just one token. But anyway, you can do it. So when you go into the parser and you are in the context where you can have an operator, you look, you see, okay, so it's a greater operator. Let's see if the next token will be again the greater operator, and then we will merge them together. So that's the second approach. And the third approach is you do the opposite, basically. So the Lexer always gives you two of those, and you look at the place where you are, and you say, not really, not really what I want. So I will separate them. So I will just kind of take half of that away as my token, and the next half I will tell the Lexer that it will be its own token somehow. We have this second approach in our Lexer and our parser. So we just have separate tokens for those operators, and we merge them. But you can do it differently. But that's the context dependent stuff, and it's always difficult. And that's why I want to avoid it in our small language here. The only context dependent stuff that well, kind of context dependent, which I allow is this, ambiguity between integers and floats, because it's really an easy one. But yeah, the real answer is avoid these situations if you can. But if the grammar is not yours, it's C++ is, well, you gotta suffer and come up with some approaches. All those approaches kind of, they're imperfect, but you gotta do sometimes ugly things. So there's no like perfect good solution. Okay, but thanks for the question. That's a good one. For the most vexing part, by the way, when you go and parse some kind of declaration, you have to choose, like, it's a declaration, and you have to choose whether or not it's going to be a variable or a function, right? So you see the type, you parse the type, you see the declarator, you go parse this name, you see an open parenthesis, and from there you're in the dark forest, because you can have either a declaration of parameter, you can have an expression there, and what it boils down to is you go kind of one path in the parser, you go, and while you can, and then you realize that you're screwed, basically, but you're in the wrong on the wrong path, in the wrong grammar production, and you just roll back and go a different path. So that's also an approach which parsers use for ambiguous grammars or C++, which is ambiguous, really. Okay, so I hope it answers the question, Stefan. Well, let's see, how many of us are here? So any other questions? Okay then. I guess we are, oh my goodness, it's an hour and a half already. So I guess we'll end here, and yeah, you will get the recording of that. Come to the next one. Thank you for coming here. And in the end, you will get the project, or maybe we will just give you the project before. I don't know. Well, can't wait for the next one. Thank you. Okay, so I guess goodbye, everybody. The next one will be in about a month, I think. So we will notify you guys. Bye.